Hello everyone, welcome to one of our online lectures for ME 5030. So this is online lecture 8, and in this lecture we will be continuing what we started in the previous lecture, which was the equations of motion for a rolling coin, a coin that is rolling without slip on a flat horizontal surface. Okay, then what my plan is to go further into the equations of motion in today's lecture, and then we will wrap it up on Tuesday's lecture, and then next Tuesday's lecture, and then on Tuesday and Thursday we will look at the spinning top, the equations of motion for a rigid spinning top, and then we will also look at non-holonomic problems such as a knife edge constraint, and how to come up with the equations of motion. Okay, so the aim for today's lecture is the following. The aim is to obtain the equation of motion of a rolling coin. Okay, and we said that we will be using the 313 Euler sequence here. Okay, and the assumptions that we have been using for this particular problem, and then something that we will be developing today to obtain the constraint equations, is that this is a coin that rolls without slip. Okay, so we're going to assume that the coin rolls without slip on a flat horizontal surface. Okay, and what is our plan? Our plan is to first establish the configuration coordinates. Okay, that's the first thing we need to do. Excuse me. And once we obtain the configuration coordinates, then we will look at the 313 Euler sequence. Based on that, we will be able to obtain the angular velocity of the rigid body, which is the rolling coin or a rolling disc. Once we have the angular velocity, then all we have to do is write the constraint equations, write the kinetic energy, the potential energy, and then we are on our way. Okay, so the steps to solve this problem. Okay, so steps for solution is the following. So the first step is obtain the configuration coordinates. Okay, then we define the Euler sequence, and based on this Euler sequence we will obtain the transformation equations from one coordinate system to the other. So transformation equations. Okay, once we have the transformation equations, then we can look at how to obtain the angular velocity of the rigid body. Okay, so angular velocity of the coin, that's the next step. Once you have the angular velocity of the coin, then we can establish the constraint equations. Okay, constraint equations. We will see whether the system is holonomic or non-holonomic. Of course, if it is non-holonomic, we need to use the multipliers. We define the kinetic and potential energies after that. Okay, kinetic and potential energies. Define that, and then we go up with the Lagrangian formulation. Okay, and the constraint equations allows us to decide whether the system is holonomic or non-holonomic. Okay, decide holonomic or non-holonomic. All right. So these are the steps. What we did in the previous lecture, and something that I will discuss very briefly today as well, is that we looked at the configuration coordinates, and we also had a brief discussion of the 313 Euler sequence, which is used to describe the rotational aspects of this rigid body. Okay, so we will look at that very quickly today. We will build on top of that, look at the angular velocity, then go into the constraint equations. Hopefully we will define the kinetic and potential energies, and then we will call it a day, and we'll come back in the next lecture, look at the equations of motion quickly, and then move on to a new problem. Okay, all right. So we start off with the figure from the previous class. Okay, so from previous lecture, from last lecture, we used the figure. We defined configuration coordinates. I guess that's not the way to write configuration coordinates. Okay, coordinates here. And here is a figure that I used in the last class. Okay, so this is the situation. I think it should fit into one page here. Okay, so this is the situation, and then we said that G is the center of mass of the coin. Okay, and G is the center of mass. And point C is the contact point. Okay, point C is the point of contact point. Of course, if we have rolling without slip, we still have the forces of static friction. So at the point C, if you look at this from a Newtonian perspective, then there's going to be the normal force of contact. Then we are also going to have the friction forces in two directions. Okay, there's going to be one in the EY direction, one in the EX direction, and the normal force in the EZ direction. All right. So from last class, we said that, okay, this capital EX, EY, EZ is a fixed frame, as you can see. And then based on that, I can define the configuration coordinates as the following. Okay, so configuration coordinates are the following. One is the location of the center of mass, which is going to be X, Y, and Z. Okay, so location of center of mass, that is X, Y, and Z. Location of center of mass, which is X, Y, and Z. And then the angular quantities that describe the precession, the nutation, and the spin of the coin. Okay, the angles, which we called as phi, theta, and then psi. Okay, these define the following. Okay, phi was defined as the precession angle. Okay, phi was precession. Then theta was called as a nutation, and then psi was the spin angle. Okay, these are the angles that we discussed in the last class. So we have 6 configuration coordinates, and the idea is, okay, how do we come up with the constraint equations and so on, and that is the thing that we're going to build upon today. Okay, so first thing is we start looking at the Euler sequence, which is used to describe the angular velocity of the rigid body. Okay, so we make use of Euler angles. And essentially this phi, theta, and psi are the Euler angles that we're defining here. Make use of these Euler angles, which we call as phi, theta, and psi, to describe the angular orientation of the body at any instant in time. Okay, and this Euler angles, we're going to look at them in the form of a sequence, which is called as the 3-1-3 sequence. Okay, so this sequence of rotations followed for this problem is the 3-1-3 sequence. Okay, and here is the 3-1-3 sequence. We start off how the sequence is performed is the following. Okay, we start off with what is called as the reference configuration of the coin. Okay, so first thing, we start with the reference configuration of the coin. Okay, and we had mentioned this in the previous lecture. In this position, the coin is called as a sleeping coin. Okay, so this is the sleeping coin, and in the reference position, the coin is lying flat on the xy plane. Okay, so essentially the coin lays flat on the xy plane. Okay, then what we say is, okay, if I have to perform the first of the 3-1-3 sequences, I take the coin and then I rotate it about the 3 axis or the EZ axis. Okay, so we rotate coin about the EZ axis or the 3 axis by an incremental rate of phi dot. Okay, and we had also mentioned briefly in the last class that the x-axis is typically called as the 1 axis, the y-axis is called as the 2 axis, and the z-axis is called as the 3 axis. Okay, so using that, we come to this following figure. This is a figure that I had used in the previous lecture. So if I bring that out, I have the figure here. Okay, so this is the figure. I'm sorry, this is not the figure that I want right now. That's the one for the next sequence. So I have the flat coin. So in this situation, the coin is lying flat on the xy plane. Okay, so I'm going to call this as the ex, ey, ez coordinate frame. So this is going to be ez. Okay, and then this is going to be e little x, and then this is going to be e little y. Okay, then we say that, okay, I take the coin, excuse me, and then I rotate it by this amount of phi about the EZ direction. So the rotation is performed in the following sense. Okay, so this is the rotational rate that is defined as phi dot. Let me write the phi dot carefully. So this is phi dot, and so what happens is that the EX axis is now going to come to a new position, which we call as the E1 prime axis. Okay, so I'm going to call this as E1 prime, and then I have the EY axis, which comes to another new position that you're going to call as E2 prime, and then the E3 prime axis is the same as the EZ axis. Okay, so this is the E3 prime axis, which is the same as the EZ axis, and this is the first of the 3 rotations that we typically give. So we start from the reference configuration, and then we go to this new configuration, rotating it by an angle which we call as the angle phi. Okay, and this vector also rotates by an angle phi. All right, and so in this particular situation, we want to see, so this is the first rotation. Okay, so let me say that this is the first rotation of the sequence. So the first rotation of the sequence about the EZ axis or the 3 axis. Okay, and what I want to do here is, now I want to represent the E1, E2 prime and E3 prime vectors in terms of EX, EY and EZ by means of a coordinate transformation. It's fairly straightforward and trivial, as you will know. Okay, so if I look at it this way, let's say that here is my E1 and E2 prime, and then EX and EY coordinate frame. So if this is going to be EX, and then this is going to be EY, right? I'm just looking at it in the planar perspective. Okay, this is EX, and then this is EY, and then if I draw the E1, E2 coordinate frame, so they're going to be somewhere here. Okay, this is E1, and then this is the E2 coordinate frame. So this is going to be E1 prime, E2 prime, this angle is phi, this angle is phi, and then the rotation is performed about the third direction. Okay, so this direction is going to be the same as EZ, which is the same as E3 prime, and the rotation rate we say is an incremental or an infinitesimal rotation rate, which is phi dot. Okay, and it's quite obvious to see that if I take E1 prime and split it into components, right, I'll just do that for E1 prime. Okay, if I take E1 prime and I split it into components along EX and EY, so if I do that here, okay, that's going to be the following. So this term is going to be cosine phi, okay, and that's cosine phi, and then this term here is going to be sine phi, okay, which means that E1 prime is going to be cosine phi EX, sine phi EY, and then 0 EZ. Right, that's fairly straightforward to see. I can likewise say that E2 prime is going to be, if I take E2 and I split it into components along EX and EY, I'll see that E2 has a component along the negative EX direction, so that's going to be minus sine phi EX plus cosine phi EY plus 0 EZ, because it is on the planar EX EY coordinate frame. Okay, and then E3 prime, it's going to be 0 EX because it does not have any component there, 0 EY, and then 1 times EZ. Okay, this is the coordinate transformation that is happening here, which means that I can take E1 prime, E2 prime, and E3 prime and write it in terms of EX, EY, and EZ as the following. Okay, so this implies that in the first sequence of rotations, E1 prime, E2 prime, E3 prime, okay, this is equal to the following. And let me make sure that this is straight. Okay, so here is my matrix, which I'm going to write as cosine phi sine phi 0 minus sine phi cosine phi 0 0 0 and then 1. Okay, and I'm going to close this bracket here. And this will be multiplied by the unit vectors EX, EY, EZ. Okay, and this is the first of the 3 rotations that we do. So this is the first rotation. I just want to rewrite that again. So this is the first rotation, and it's about EZ, or the 3 axis. All right, and once again, just to recap this idea here, I take the coin in the sleeping position, so this is called as a sleeping coin. Okay, this position is called as the sleeping coin, as we have labeled in the above situation. Sleeping coin, and this is the reference position for the coin. Okay, and then we take the coin, rotate it by an angle phi, we get a new coordinate frame. This is once again a body fixed coordinate, which means that it's rotating a co-rotational coordinate basis, which is rotating with the body. Okay, so this is the situation we end up with. So this is the first rotation that is performed. Okay, then we go to the second situation. So we start with the reference configuration, the sleeping coin, and then rotate the coin about that situation. Then we go to the second one. Okay, in the second configuration, okay, we take the coin, after the first rotation has been performed, and we next rotate the coin Okay, we next rotate the coin about the E1 prime axis, which is the new 1 axis, and this is going to be called as a 1 axis rotation. Okay, because you're doing it about the E1 prime axis, it does not matter whether it is prime or not, but because it is about the 1 axis, it's called the 1 axis rotation. So in this situation, I take the coin, I start off with the first rotation, and then I come up with the primed coordinate frame. Then I take the primed coordinate frame, rotate it about the E1 prime direction, I get the next situation. Okay, so here is the next situation. So I look at the coin here. Okay, so here is the coin after the rotation has been performed. Okay, now we got to start labeling these axes. So my original axes are the following. Okay, so I'm going to have the original axes as I'm sorry, this is going to be, once again, this is going to be E1 prime. Okay, and then this is going to be E2 prime, and then this is going to be E3 prime. Now I'm going to take the coin and rotate it about the E1 prime direction by an infinitesimal or incremental amount of theta dot, and so this tells me that E1 prime will be coincident with E1 double prime. Okay, or maybe let me expand the figure a little more so that I have some space to write in here. I should be able to do that, I think. Okay, alright, so I'm going to take these guys and write them a little better. Okay, apologies for doing these again, but I want to collate all these results together. So first I had E1 prime. Okay, this is E1 prime, and this will be the same as E1 double prime. This is going to be E2 double prime, which means that this is a rotation of an angle theta. Okay, and then this creature here is going to be E3 double prime, and you'll see that this rotation is by an amount theta as well. Okay, so I have the rotation rate theta dot about the E1 prime or the E1 double prime direction. So this is going to be called as the second rotation. Okay, the second rotation. Performed about the E1 prime direction by a rate theta dot, and so this is also called as a 1 axis rotation, which means that previously I had a 3 axis rotation, now I have a 1 axis rotation, and then we will see that okay, we can once again write the transformation equation. So now when I do the transformation equations, I want to be careful. So when I'm looking at the way the axes have been transformed, so look at the axes, and the way I'm looking at it is by seeing the E1 prime axis coming towards me, so that if this was the E2, E3 prime axis, so look at this is going to be my E3 prime, that's going to be my E2 prime directions. Okay, this is E2 prime, this is E3 prime, then I'm going to have excuse me E2 double prime, and then I'm going to have E3 double prime excuse me, and then these are all going to have this direction which is coming out of the page, which is going to be my E1 prime, which is the same as E1 double prime. Okay, and the angle that we're going to be seeing here is the angle theta, and this is also the angle theta. Okay, and if I take this E2 double prime, split it into components, you can see what happens, right, quite easily. Excuse me. So these are the components along the E2 prime and E3 prime direction. So this guy is going to be cosine theta, and that's going to be sine theta. And likewise, I can do the same thing for E3 double prime as well. So if I write the transformation equations now, okay, transformation equations for the second rotation, I get the following. Okay, I have E1 double prime is equal to, if I write it in terms of E1 prime, so that's going to be 0 E1 prime, and then I'm going to have cosine theta E2 prime, and then sine theta E3 prime. Okay, I just want to write this E3 properly. Then if I do the same thing for E2 double prime, that's going to be 0 E1 prime minus sine theta E2 prime, okay, plus cosine theta E3 prime. And then lastly, I have E3 double prime is going to be, I'm sorry, I made a mistake here, so I have to get rid of some of these terms here. Actually, apologies for that. Okay, so maybe before I do that, I just want to rewrite and say that, okay, this is E2 double prime, and this is actually E3 double prime, and then so this is going to be E1 double prime. Okay, E1 double prime is going to be 1 times E1 prime, 0 times E2 prime, 0 times E3 prime. All right, which means that if I now write this as a matrix, okay, so to write the rotations in the matrix form, which means that I'm going to have the following: E1 double prime, E2 double prime, E3 double prime is equal to, okay, the following matrix, which is called as the rotation matrix here. This is E1 prime, you see, is 1 0 0 0 cos theta sine theta, 0 minus sine theta and cos theta. Okay, and you can see that I have to multiply this by E1 prime, E2 prime, E3 prime, and I want to give it the same labeling as before, so I'm just going to scoot up and perform the look at this one here. So I'm going to bring this guy right down. Okay, so I'm just going to copy that and bring that here. Okay, so this is going to be the second rotation now, not the first rotation. So the second rotation performed about the E1 prime direction. Okay, this is going to be about E1 prime direction, or the one axis now. This is called the one axis. Okay, and it's important that we see that this basic idea is just getting carried out again and again. So in summary, maybe I can scoot this and bring it to the previous page. Let me try that. Okay, let me try doing that. I think it should be able to fit here. It should, if I can bring these creatures up a little bit more. And let me do that. Okay, apologies for all that. I think I just wanted to make sure that we have all the information that we have in the spot that we want it to be. Okay, so I'm just going to scoot these all up a little bit more so that we have everything going on for us. This is the second rotation. Okay, So in the second rotation, what we have is we bring the coin from the first configuration, and then we say, okay, I'm going to rotate it by an angle theta. And as I rotate it by an angle theta, I'm doing the rotation about the 1 prime axis. So E1 double prime is the same as E1 prime, and then I have E2 prime, E3 prime, E2 double prime, E3 double prime. Okay, and just as a note, E3 prime was the same as the EZ axis from before. All right, and then we said that okay, these can be expressed in the matrix form in the following manner, and which is exactly what we did here. Okay, I wrote E2 double prime first, and then E3 double prime, and then E1 double prime, and the matrix form is written this way. All right, we come to the last rotation. Okay, slightly tricky, and here is the deal. Okay, so what we do is the following. Now in this figure you'll see that here is the contact point, as you can see there. Now what I want to do is of course the thickness of this coin is really small, so we're going to neglect the thickness of the coin as such. Okay, so we assume the coin to be very thin. So this is a thin solid disk. And so we say that this coordinate frame E1 double prime, E2 double prime, E3 double prime is not a co-rotational basis. So for the sake of simplicity, we say that the frame E1 double prime, E2 double prime, E3 double prime is embedded in the coin but not rotating with the coin, is embedded in the coin but not rotating with the coin. Okay, which means that it is not a co-rotational basis. And last lecture we said that a co-rotational basis is something that is fixed to the coin and rotating with the coin. What is the reason for doing so? The reason for doing so is because we want to capture the location of the contact point C relative to G by making use of this E2 double prime vector. Okay, the reason for that is the following. Okay, reason for this is we want to represent the contact the position vector from contact point C to center of mass using the E2 double prime unit vector easily. Okay, and you'll see the reasoning for that. So what we do in the third sequence of rotation, okay, so which means that for the third rotation in the sequence, we say that okay, instead of rotating this E1 prime double prime E2 double prime E3 double prime direction, we take a coordinate frame that is equivalent to E1 double prime E2 double prime E3 double prime, such that the moment of inertia matrix defined with respect to that does not change, and then we characterize the spin of the coin by rotating, by saying that that new coordinate frame is at an angle of psi with respect to the double prime frame. Okay, so for the third rotation in the sequence, we consider a new frame which I'm going to call as E1, E2, E3 with the origin at the center of mass. Okay, with the origin at G, such that the moment of inertia defined with respect to the E1, E2, E3 frame is the same as that defined with respect to the E1 double prime, E2 double prime, E3 double prime frame, which essentially means that E1, E2, E3 and E1 double prime, E2 double prime, E3 double prime are both principal frames. Okay, and we say that so we can make that statement as well. So the frames E1, E2, E3, and I'll show you E1, E2, and E3, and E1 double prime, E2 double prime, E3 double prime are both principal axes for the coin, are both the principal coordinate frames such that the moment of inertia defined with respect to these frames is a diagonal matrix. Okay, such that the moment of inertia tensor defined based on either of these two frames is a diagonal matrix all right. So this is then we say that okay, to capture the spin we say that these two frames are separated by an angle psi. Okay, so to capture the spin of the coin we say that the two frames are separated by an angle psi and the rate of rotation is defined with respect to the E3 double prime frame. Okay, and the rate psi dot is defined with respect to the E3 double prime frame. All right, so lots of things that we have been writing down here. Okay, so we say that the coin is very thin, and then for simplicity we say that the frame E1 double prime, E2 double prime, E3 double prime is embedded in the coin, so this is body fixed and not co-rotational. The reason being we want to define the contact point, the position vector from the contact point to the center of mass of the coin as using the E2 double prime unit vector. Once we do that, then we say that okay, in order to capture the spin of the coin, because the coin has to spin as well, right? The coin is having a precession rate, it has a nutation rate or a lean angle, and then it has a spin rate. And to define this, we have another coordinate frame which is having the same moment of inertia matrix as this double prime frame, but separated from it by an angle psi. Okay, and here is the situation for us. Okay, so the third sequence of rotation is about the 3 axis now. Okay, so notice that. Okay, note that the third rotation is about the E3 double prime or the E3 axis at a rate of theta dot. So this is the 3 axis rotation. Okay, and then the figure that accompanies this is the following. So I'm going to consider the same figure as before. Okay, so you can think of this figure here. Okay, I'm just going to bring that creature once again, and I'm going to label the axes from before. So here is the prime axis. Okay, so this is E1 prime. So let me write that down a little carefully here. So this is E1 prime. Then we call this axis as the E2 prime axis. This was the E3 prime axis, which was the same as EZ, right? And then I'm going to have the next set of axes, which we called as E2 double prime. Okay, then this was E1 double prime, and then we said that this creature was E3 double prime. Now I'm going to say, okay, hey, I'm going to be doing the spin of the coin about this direction by a rate psi dot, which means that I'm going to call this as the E3 axis, and so I'm going to have a new set of axes. Okay, so let me draw that out here. So one here, and I need to make sure that this is at the center, of course, right? Then I'm going to have so this is with respect to the E1, then I'm going to have one with respect to the E2. They're on the same plane as the E1 double prime and the E2 double prime, so this is going to be defined by the following angles. So that's the angle psi. Okay, and of course this is the same angle psi. Okay, and this direction is going to be E1. This is going to be E2. Okay, and if you want this from a two-dimensional perspective, then essentially here is what the situation is. So if I draw E, let's say this is E3 prime and E2 prime, this is E2, then this is E1 double prime. Okay, this is E1 double prime, this is E2 double prime, and then I have E3 double prime, which is coming out of the page here. Okay, this is E3 double prime. Now we're going to say that this is the same as E3, and then I'm going to define an E1 direction and an E2 direction here. Okay, so this is going to be E1, this is going to be E2, and this is the angle psi, this is the angle psi, and this is the rotation rate psi dot. Okay, this is exactly what you have seen in this figure here as well, and you can pretty much see that if I do the coordinate transformations, if I take E1 and then split it into components along one direction versus the other, here is what I end up getting. Okay, so E1 is going to be cos psi E1 double prime sin psi E2 double prime 0 times E3 double prime. E2 is minus sin psi E1 double prime cos psi E2 double prime 0 E3 double prime, and then E3 is the same as E3 double prime. Okay, this is going to be the third rotation in the sequence. Okay, this is the third rotation about the E3 double prime, which is equal to the E3 axis, or the 3 axis, at a rate of psi dot, which depicts the spin rate of the coin. All right, and once I have that, then I can write the matrix form of this transformation in the following way. So this is going to be E1, E2, E3, and you'll see that, okay, here's my matrix box. That's going to be cos psi sin psi 0 minus sin psi cos psi 0 0 0 1. Okay, and this will be multiplied by the column vector e1 double prime, e2 double prime, e3 double prime. So we are almost there. Okay, this is the third rotation, and so I'm going to start collating all these rotations. Okay, so far here is what we have. Okay, so story so far. Okay, rotation performed about the EZ direction at a rate phi dot, then 2. This is called as the first 3-axis rotation. Okay, then the rotation performed about E1 prime direction at a rate of theta dot. This is the second rotation. This is the first rotation. It's called a 3-axis rotation. Second rotation, this is a 1-axis rotation. And then third one is the rotation performed about the E3 double prime, which is the E3 direction at a rate psi dot. This is the third rotation, and this is a 3-axis rotation. And so you see that, okay, the first rotation is a 3-axis rotation, the second is a 1, the third is a 3-axis rotation, and so this sequence is called as the 3-1-3 Euler sequence. 3-1-3 Euler sequence. Okay, and this is for me, this is the most easiest way to visualize the motion of rigid bodies. But if you're in the aerospace industry, then typically the 3-2-1 sequence is also very popular, probably more popular than the 3-1-3 Euler sequence. All right, now what I'm going to do is I'm going to collate all these figures and have the transformation equations written down next to them. Okay, so I'm going to look at all the figures, the transformation figures. Okay, so combine or collect all the rotation figures. Okay, so that we have them in one place. Pardon me for doing this. I know that sometimes it can be a little boring. So here is the first one that I'm going to see. I'm going to take this guy. Okay, this is the first one. Okay, so copy that and bring that down here. Okay, so this is the, I guess I should be pasting the image, the first rotation. Okay, then I come to the second rotation, which we had the figure for here. Okay, so I'll copy this and bring that down here, and then we will label these again. Okay, this is the second rotation. Okay, and then we have the third rotation, which we had here. Okay, copy and then paste it down here. I'm sorry, I had to paste the image. This is something that I typically keep forgetting. Okay, all right, so this is the 3-1-3 sequence. So just as a situation of labeling, this is the first rotation. Okay, then this is the second rotation. this is the third rotation. Okay, and so in the first rotation it's about the z direction and the rate is phi dot. Second rotation the rate is theta dot about the E1 prime. The third rotation the rate is you can see it's psi dot about the three directions. I just want to scoot this figure up. I guess this is all I can do here. Okay, anyways, this is fine. All right, and then what I can say is the E1, E2, E3 rotations, they can be written in the following form. I want to collect all the rotation matrices as well, so that's my next step too in this problem. So I start off with the E1 prime set of things. Okay, so here is my setup, so I'll just copy that and then I'll bring that down here. Okay, and so here is what I have. So that's the first one. Okay, then I'm going to have the second one, which I'll bring down here as well. Okay, the double primes. Copy that, and then I'll bring that down here. Okay, so that's the second one, and I guess I need room for the third one. So to do that, I'm going to take all of these guys and then move them up a little bit. Okay, move them up. I guess I can't do that. Well, that doesn't look too great to me, so I'll just keep these things here. Let me just squeeze in the third one somewhere down the road. Okay, so here is the third one. And I'll write them in a much more succinct form. Okay, and here is the third one. Okay, so I did not collect all of them together, but here is what I want to show. So here this character, so maybe I can scoot this down a little more so that I have more space to do my writing. Okay, so here is what I want to say. I'm going to call this as the following. Okay, this is going to be called as E prime 1, 2, 3. This is a column vector that's equal to R1 times E x, y, z. Okay, so in this the labeling is that this is a column vector. This is also a column vector. Okay, and this is the first rotation matrix. Okay, likewise I'm going to do the same thing for this one. I'm going to call this as E. Now this is the double prime, and 1, 2, 3 is equal to R2 times E prime 1, 2, 3, and once again the same nomenclature holds. This is a column vector. This is also a column vector. Okay, and this is the second rotation matrix. All right, and then I have likewise the third one here, which means that I can write these things a little more easily. So I have E 1, 2, 3 is equal to R3 times E double prime 1, 2, 3, and likewise this is a column vector. That's also a column vector, and this is the third rotation matrix. Okay, all right, so I have all of these things collected, and so I just want to rewrite these things and say the following. Okay, so I have first of all E prime 1, 2, 3 is R1 times E x, y, z. E double prime 1, 2, 3 is R2 times E prime 1, 2, 3. But E prime is R1 times E x, y, z, so this tells me that E double prime 1 2 3 is r1 times r2 times e x y z. Okay, all right, so that's another key thing that we have here. And then I come to the last one, which tells me that, okay, e1 2 3, which was r3 times e double prime 1 2 3, this tells me that e 1 2 3 is going to be r1 times r2 times r3 times e x y z. Okay, these are all key things that we're going to be marking, so I want to put a box around each of them. Okay, so here is one, that's the first one, okay, which we're going to be making use of. Then here is the next one. Okay, and you can immediately see that the Euler sequence of rotations is given by the rotation tensor for the Euler sequence is given by the set of three rotation matrices r1 r2 r3. Okay, and then here is the third one. Okay, let me write that out properly. All right, so these are three things that that are fairly important in our analysis. I can also say the following. Okay, so if I call this as A, and if I call this as B, and if I call this as C, okay, then we also have the following. Because these are rotation matrices, they're orthogonal, which means that, you know, I can take their inverse and it becomes the same as their transpose, which tells me that E xyz is the same as r1 transpose e 1 2 3, and then this is e prime 1 2 3, pardon me for that error. Okay, this is e prime 1 2 3. Then I can say that e prime 1 2 3 is going to be the same as r2 transpose times e double prime 1 2 3. Okay, that's something that is also true. And then lastly, I can say that, you know, e double prime 1 2 3 is going to be r3 transpose times e of 1 2 3. And these are also fairly important equations which we will be making use of. Okay, as we go further. I gotta get rid of this guy. Sometimes I can't draw straight lines. I'm sure it is equally frustrating to you to see me waste time on these trivialities, but you know, we want to write this a little nicely and neatly, right? There's a sense of satisfaction in doing that. Okay, all right, so this I'm going to call as equations ABC. This is equation D. Okay, equation D, equation E, and equation F. So equations A, B, C, D, E, F characterize the entire sequence of rotations from one basis vector system to the other for the 3-1-3 Euler sequence. Okay, so let me make that statement. So equations A, B, C, D, E, F characterize the set of rotations that make up the Euler sequence, the 3-1-3 Euler sequence. And of course, if you chose a different set of rotations, if you chose the 3-2-1, then the rotation matrices that you end up with will not have the same form as what you're seeing here. They will be slightly different to look at, but the qualitative aspects of the problem will not change. Okay, you'll still be able to come up with a set of equations of motion for the problem, and you'll be able to study it under the umbrella of the angles that you have defined for that particular sequence of rotations. All right, so we have done a lot of things here so far. Of course, some of them seem like repeated writing, but here is this first set of rotations about the phi dot direction. Then the second set is about the E1 prime direction, and then the third is about the E3 direction, which means that I can now write the angular velocity vector for the body as follows. Okay, so first of all, let's call these as names. So something that I want to say is the E prime system, so notations. Okay, we will say that the EXYZ, we will call this as frame F1. Okay, then E prime 1 2 3 is frame F2. Okay, then we will say that E double prime 1 2 3 is frame F3, and then the E 1 2 3 is frame F4. Okay, these are the different frames that are fixed to the body. And then also E capital X, E capital Y, EZ is frame F0. This is a fixed observer at the origin of this frame. And see figure on page 1. Okay. Excuse me. All right, now I say that, okay, I'm going to define the angular velocities of each of these frames with respect to the fixed frame F0. Okay, I'm not worried about the frame F1 because at that point in time, for me, the frame F1 is coincident with the frame F0, so I don't have any particular angular velocity defined to that frame, so I can make a note and say that, okay, this is coincident with the frame F0, which means that this is actually a body frame, but it's not rotating with the body. Okay, so this is fixed to the body but not rotating with the body, so I can define the following angular velocities. Okay, so angular velocities are defined in the following manner. So angular omega of frame 2 with respect to frame F0. Okay, this is going to be defined in the EZ direction, so this is going to be phi dot in the EZ direction, and I want to make a note. Okay, note frame F1 is fixed to the coin but does not rotate with the coin. Which means that it is coincident with F0, which also tells me that, you know, omega of F1 slash F0 is equal to 0. Okay. All right. So omega of F2 slash F0 is known to me, which is the same as F2 slash F1. So I can say that, you know, okay, omega of F2 slash F1 is the same as omega of F2 slash F0, and this is going to be phi dot in the EZ. Okay, then I'm going to have omega of F3 slash F2. This is the second rotation. So here was the first rotation in the sequence about the 3 axis. Okay, then omega of F3 slash F2, you know, this is going to be in the theta dot E1 prime direction, or which is the same as the E1 double prime direction if you want to write it this way. So this is the same as E 1 double prime as well, and this is going to be the second rotation, okay, about the 1 axis. And then I have lastly, and of course I see that if I have f3 with respect to f2, I can write f3 with respect to f0 as the following. So this tells me that omega of f3 with respect to f0 is f3 with respect to f2, f2 with respect to f1, f1 with respect to f0. Of course f1 with respect to f0 is gone, it's a 0, which tells me that omega of f3 with respect to f0 is going to be the following. It's going to be phi dot in the Ez plus theta dot in the E1 prime direction, or I can write it in different ways. Okay, this is also the same as phi dot in the Ez is the same as E3 prime, so you can leave it that way, or this is theta dot in the E1 double prime direction. Okay, that's the same thing here. Then I come to the third one, okay, which is omega of f4 slash f3. Okay, this is going to be psi dot in the E3 double prime direction, or psi dot in the E3 direction, and we call this as the third rotation about the 3 axis. And you see why the name is a 3-1-3 rotation, right? The first rotation about the 3 axis, the second rotation, first rotation about the 3, second rotation about the 1, the third rotation is about the 3 axis again. Of course, it's not the same 3 axis as you started off with. Okay, this is a different 3 axis. Okay, and so if I go forward and do the next step, then I see that omega of f4 slash f0 is omega of f4 slash f3, f3 slash f0, which I had in the previous step. And so this essentially is going to be omega of the rigid body. Okay, this is omega of the coin. Okay, which means that omega of the coin is going to be phi dot Ez theta dot E1 prime, and then psi dot in the E3 double prime, or another way of writing this is omega of the coin is going to be phi dot in the Ez, it's going to be theta dot in the E1 double prime, and then psi dot in the E3 double prime, or the same thing. These are all the same thing. Okay, omega of the coin can be written as phi dot in the E3 prime direction, theta dot in the E1 double prime direction, psi dot in the E3 double prime direction. Okay, they are all the same things. Okay, all the same, and this is mostly because Ez is the same as E3 prime, E1 prime is the same as E1 double prime, and then E3 double prime is the same as E3. Okay, all right, and there are a couple of important points that I want to make here. Okay, and then we will proceed a little further, and then we will call it a day. We'll come back and then wrap this up in the next lecture. Okay, the couple of things that I want to mention are the following. The first thing is this. Okay, there is a physical singularity. This is something that we had discussed in the previous lecture. Okay, at the reference configuration of the coin, let me write this carefully. Reference configuration of the coin has an infinite number of points infinite number of contact points. Okay, let me write that as, express that as contact points, which represents a physical singularity. Okay, this represents a physical singularity, Okay, that's an important thing, because there are an infinite number of contact points. We really do not know if the coin is rolling or not, and the fact that the coin is planning to roll is the saving grace for us. Okay, then here is another thing that I want to see. Okay, look at this. If in the second rotation of the 3-1-3 sequence, the angle theta is 0 degrees, or if theta were 180 degrees or pi radians, then we then we would not be able to distinguish between the phi dot and the psi dot rotation rates. Okay, so if I go back to that figure, okay, so I just want to reread this statement. So if in a second rotation of the 3-1-3 sequence the angle theta is 0, or if angle theta is 180 degrees, then we would not be able to distinguish between phi dot and psi dot rotation rates. Okay, this is a knot here. We would not be able to. And the idea is this. Okay, if I go back and look at the second rotation, let's take a look at the second rotation. So in this rotation, if I had set theta to be equal to 0, then what would happen is that the coin would start looking like the sleeping coin. Okay, which would be similar to the reference configuration I started off with. And in that configuration, if I gave a rotation rate of psi dot, then it's kind of meaningless, right? Because psi dot and phi dot will be the same. Okay, and this is exactly what I mean by saying that, okay, if I go back and set theta is equal to 0, then it's going to be the same as phi dot and psi dot being in the same direction. So in this, what I want to show or specify is that this is the second rotation. The angle, if theta is equal to 0 degrees or pi or 180 degrees, okay, that represents a geometric singularity. Geometric singularity. All right, and I want to write that statement down here too. Okay, so when we come back here, so this implies that for theta is equal to 0 or pi, then we have a geometric singularity. Okay, and this is true of pretty much all the sequences of Euler rotation. If you take a different sequence, then you're going to have a different control angle that will end up having a geometric singularity at certain values, and you will not be able to distinguish between the spin and the precession rate. So once again, if you have a geometric singularity, okay, so geometric singularity, for the let me rewrite this again. For some reason, as I'm writing more and more on the iPad, my handwriting is getting to become garbage. Okay, so geometric singularity for theta 0 degrees or pi degrees or 180 degrees. I always importantly in the 3-1-3 sequence, that's important. I mean, this is not true for any sequence. Okay, for a different sequence you'll have a different set of singularities. In the 3-1-3 sequence, Euler sequence, the spin rate psi dot and the precession rate phi dot will become coincident, which is not a good thing. Which means that we are losing information. We will not be able to distinguish between the precession and the spin of the coin. This is absolutely not a good thing. So we want to avoid the geometric singularity. So we typically choose an angle of theta between 0 and pi. Okay, so to avoid this, to avoid the geometric singularity, we choose an angle of theta that is between 0 and 180 degrees, which means that theta is greater than 0 and less than 180 degree. Okay, so the two things that we have discussed here are the physical singularity, where we say that in the reference configuration the coin is going to have an infinite number of contact points. That is not a good thing for us. Then we have the geometric singularity, where the spin and the precession rates become the same. Okay, so that is not something that we would like to have as well. Okay, so going forward, what are the things that we want to see? So of course we are going to choose theta that is not going to be either 0 or 180 degrees, so that's not going to affect us in any great detail, but I just want to make sure that we all understand and we are all on the same page here. The third thing that I want to actually write out here, the third thing, if we look at the angular velocity, the angular velocity of the coin, omega coin, is equal to phi dot E3 prime plus theta dot in the E1 double prime and then psi dot in the E3 double prime. We see that the direction E3 prime is not perpendicular to E1 double prime or E3 double prime, which means that E3 prime, E1 double prime, E3 double prime do not form an orthonormal basis. That is, they are not going to be perpendicular to each other. The dot product between E3 prime and E1 double prime is not going to be 0. So this means that this is actually called as an Euler basis. Okay, so this is called the Euler basis for a 3-1-3 sequence, and the Euler basis is not necessarily not an orthonormal basis. Okay, something that I just wanted to write out. Okay, this is not a huge deal, but I just want to make sure that we are aware of this taking place. Okay, now what are the steps to go forward in this problem? I'll be looking at these in the next lecture, because I think for the past 2-3 lectures I've been taking up a lot more of your time, so I want to be a little more succinct for the next lecture. So what I want to do is I will be writing omega in the XYZ coordinate frame. Okay, I'll be converting E3 double prime and E1 double prime into the EX, EY, EZ coordinate frame, and so that's my next step. Okay, so in the next lecture we will be writing omega of the coin in a consistent basis, that is omega coin in the XYZ or double prime system. Okay, This will be done by using coordinate transformation. Coordinate transformation, or the rotation matrices that we have used or we have obtained in the above set of things. And then the next thing is we will be looking at the roll without slip constraint, and we will prove that this is non-holonomic. We will prove that this is non-holonomic. Okay, and then my next step is to write the Lagrange formulation using Lagrange multipliers. Okay, write the Lagrange formulation for the rolling coin using Lagrange multipliers. Okay, that is the last thing that we will be doing. Okay, and once we're done, we will be able to obtain the equation of motion. Okay, so this will gives us the equation of motion. Of a rolling coin. Alright, so most of the hard work has been done. The hard work was done in obtaining W coin. Okay, this was the most difficult part here. Okay, so that is the most difficult part. Once we have that, then we have all the coordinate transformation matrices. Writing the angular velocity in a consistent basis is not a big deal. Rolling without slip is a vector equation which we can make use of, fairly straightforward. And you will see that just by looking at that constraint equation, it's going to be tremendously formidable, and it will make absolute sense to say that this is non-holonomic without even doing the test for integrability. I'm going to be probably skipping that in the interests of time. And then lastly, the Lagrangian formulation has to be written using the kinetic and potential energies, and we will be on our merry way, find the equation of motion. Okay. Thank you for your patience. I hope all of you are staying safe and healthy. I'll be happy to answer any questions you have via email or on Carmen. Your exam is due on Thursday by 12:30 p.m. I hope the exam was fairly straightforward to all of you. Okay, take care of yourselves. Bye-bye.